We're delighted, we're delighted to have Sha Jiang here to give a brown bag. Sha Jiang is a graduate student at Stanford. She began her studies in sociology in Wuhan and did a master's in demography there before coming to Stanford, where she's actually a student in biology. Her main focus is demography, and Tulcha is her advisor. And this is work in progress, isn't it, from your dissertation? Maybe
part of the dissertation.
Part of the dissertation. She's a fourth-year student and will be finishing this year or next.
Yes.
We hope you enjoy her talk, can give her lots of feedback, and can get to know her by this introduction. So thanks so much for agreeing to come and give a talk in person. We look forward to it.
Thank you so much for the introduction, Josh. So it's not my first time to attend the brown bag seminar, but it's first time that I attended as a presenter. And I really appreciate this opportunity because it's valuable for like graduate students. So today I will be introducing one of our ongoing work called How Do Changing Vital Rates Influence Kinship Networks? My collaborators include Dr. Wenjun Zhou and Dr. Shrika Tojaperka from Stanford, and Dr. Zheng Guo from Huazhong University of Science and Technology, and Dr. Hal Caswell from University of Amsterdam. So the kinship network we analyze here is defined as the direct, matrilineal, and consanguineal relationships, such as mother, aunts, sisters, cousins, daughters, and nieces. This topic is important because in modern society, kinship networks have considerable effects on different aspects of demography, such as intergenerational support and inheritance. And moreover, kinship network also serves as an important source of information in traditional society. So it has effects on people's life decisions, such as where to find a job, where to find a mate. And in addition, this topic also has various implications on different disciplines, such as psychology, criminology, and psychology. And from a demographic perspective, we know that kinship network is shaped by both mortality and fertility rates. One indicator that can be used to quantify the change in those vital rates is the net reproductive rate, R0. R0 is a function of Lx and Mx, where the Lx is the probability of living to age X, the one in that table, and Mx is the average fertility for daughters of a woman of age X. And this indicator R0 is quite similar to another more well-known indicator in demography, which is the total fertility rate. For total fertility rate, it only depends on the Mx fertility, while R0 is survival weighted fertility. So it considers the change in both mortality and fertility rates. So the model we use to calculate the kinship network, it starts from the most fundamental work in this area by Goodman, Kifis, and Pollum in 1974. In that paper, they used integral equations to calculate the expected number of kin of a focal individual at different ages. And later on, Caswell and his colleagues, they used matrix operations to calculate not only the expected number, but also the age distribution of kin for both living and dead kin. The logic in the Caswell's model is they treat each type of kin as a population and do the population projection. So for example, the number of kin of focal at time t+1, called kt+1, depends on the number of kin at time t, kt, and the survival of this type of kin, then plus the number of new kin produced from time t to time t+1, which is the beta t. And beta t is 0 for kin such as mother, grandmother, great-grandmother, older sisters, and so on. Because after focus the birth, there will be no new such kin produced. But beta T for other types of kin is non-zero, and it depends on the fertility of another type of kin. For example, the number of new granddaughters depends on the fertility of daughters. And I have to note that some of the papers, they call the focal individual as focal, and others they call it ego. So in the presentation, I would use these two terms interchangeably.
Are you going to use this equation later on?
Yes.
Okay. Why doesn't beta also depend on capital K? I see survivorship is going to depend on K. Why doesn't the number of new nieces depend on the number of sisters you have?
Yeah, it depends on K and also the fertility of that.
So this expression beta T has K somehow in it?
Yes, it's like a fertility matrix types. Like for the granddaughter is the fertility of daughter and then times the K for that daughter. Does that make sense?
Well, it looks like, to me, it looks like one of these migration equations where we have the, a closed population being projected forward and then additive migration. But I don't think it is that, because the beta T should be multiplying. There should be some transition matrix multiplying the existing kin. But here it's just some additive thing that's independent of KT, it looks like on the right-hand side.
I think in the real calculation, it depends on KT. Maybe this is just like a simple way to note this part.
Okay.
Yeah. And then based on this logic, we use two models. The first is a time-invariant model, where we assume that all relatives, focal and focal herself, experience the same mortality and fertility through their lives. So the survival matrix and fertility matrix does not change over time. And this model enables us to do comparative statistics. Another, of course, when we change the mortality and fertility over time, we got a time-varying model. And this model is an actual dynamic model. Before we go into our hypothesis, I want to first introduce previous findings by Goodman et al. Because they also analyzed the relationship between demographic transition and kinship size in a time-invariant model. So what they first calculate is the expected number of kin ever born at age X of focal, call it K delta X. And then they got the maximum number of this expected number of kin ever born across all ages of focal, call it K eventual. So the K eventual is the eventual expected number of kin for a particular type of kin. Qualitatively, we will think this K eventual for daughters is R naught, because we have to consider the survival of the mother and then the fertility of the mother. And obviously we get R naught. But what they found is the K eventual for daughters is actually just TFR, not R naught. Because this whole model is a focal-centered model. The survival of focal is always 1. So we don't consider that focal will die. And that's why the number of daughters is just TFR. But when it comes to the number of granddaughters, it's TFR times R naught, because granddaughters are offspring of daughters. And each daughter will have R naught number of granddaughters. So it's just these two times together. And similarly, to ensure that focal will be born, the survival of focal's mother is always 1 before focal's birth. And that is to say, when we consider the offspring of focal's mother, only part of the mother's survival is considered. So the K eventual for sisters, we call it S. S is a number between R naught and TFR. And similar logic applies to the number of aunts, because of course, to ensure focal's birth, the grandmother needs to be alive to be able to produce focal's mother and then focal herself.
Why doesn't this take into account the variance?
I'm sorry, K.
You say S is between the NRR and the TFR, but the variance of the number of family size is going to mean that the average number of sisters could be a lot bigger than TFR.
I think here it's just the expected number. We don't get the distribution of the number of kin. So like some families still will have like larger sister size, but some family has smaller, but the model only gives us the mean.
Will you talk about this later, the kind of the role of variance in?
Yeah, that will
Family
be like
size?
the future work.
Okay.
So since nieces and cousins are offsprings of sisters and aunts correspondingly, so the K for those two types of kin is just S times R naught. So based on these previous findings, we have several research questions. First, what age range of focal should we focus on? Because Goodman's work, they just calculate maximum across all ages of focal. Here we thought like demographically dense ages are important. This concept comes from the paper by Redfield in 1991. Because during those young adult ages, there will be a lot of key life cycle events happening, like education, work, and marriage. And during this period, Kinship Network could have an important role by providing information or support. And then instead of kin ever born, we think living kin is of greater importance. Then instead of just a time-invariant model, what will happen in the okay. And then we get the maximum expected number of living kin when focal is at the demographically dense ages. We call this number as K.
Did you say that what maximum means? It's the maximum of the average person has different number of expected kin at
At
different
different
ages,
ages,
and
and
so
we
it's the
just-
top of it. It's the
Yeah, we
top-
just
yeah.
look at the particular age range and find the maximum number. So our hypothesis for the time-invariant model is for aunts, sisters, and daughters, we think the K is approximately R naught. And for cousins and nieces, it's approximately R naught squared. But we are not sure what the correct hypothesis will be for a time-varying model. So we first try maybe the K for different birth cohort of focal, and then the R naught for the same birth cohort.
Question here.
Yep.
Well, going way back, there was a line that said, and I guess it's, no, you don't need to go
Oh,
back,
sorry.
but that said this is matrilineal descent relative, which I suppose maybe the whole literature does that, but I can't help wondering about the bilateral kinship, and particularly with these nice little intuitive K is approximately R naught and so on. Would we have K is approximately 2 R naught if we included male descent? Aside from, age of marriage and different life expectancy and so on, but roughly, is that the right intuition or is it completely wrong?
My first impression will be it depends on SRB. Like
Depends on,
SRB, sex ratio at birth.
okay,
Yeah, like for countries
Yeah.
like China or South Korea, maybe it's not 2 R naught. And also our collaborator Hal Caswell, they have a new recent paper, which is the same model, but they extended to 2 sex setting. So they consider both males and females. So maybe we could get answers if we try their new model.
okay.
And then the data we use is from UN World Population Prospects 2022 version. We got single age interval data for every 5 years since 1950. And first, we present the kinship size from a time-invariant model. So in this figure, we have year on the x-axis and k, which is the maximum expected number of living kin when focal is at demographically dense ages on the y. And the top panel is the k for aunts, the bottom is the k for cousins, and different colors represent the result for different countries. So we first see that within each country, the changing trend of k is similar for different types of kin. But there's a huge difference between different countries. For example, the k for India for aunts, the green line, it changes very slowly. But the one in China, it first have a deep drop and then up, and then very rapid decrease.
So could you explain what, this is, assuming your model is true, these are what the calculations come up with?
Yes.
Okay.
Like each dot on the calculation just means, like for this one, we just use the vital rates from 1960 across all years, like make it constant. And
So these are like static calculations?
Yes, static, yes. We just put it together to see how it changes. And we thought this change in k should be related to the change in R0. And it is. In the right, we have year on the x-axis and period R0 on the y-axis. But just eyeballing these two figures, we see the change in k is very much correlated to the change in R0. But to further test our hypothesis, we plot k against R0 for different countries when we use vital rates from different years.
Sorry, just a missing context. The red, why does the red drop like that?
This is because in 1960, China was undergoing a great famine. So the mortality increases a lot and fertility decreases. That's why we see a huge drop there.
It's contextual, because I know like India and China prioritize like male births over female births, and like let's say abortions of female births. Does Japan have that kind of context too, or?
I don't think Japan has an imbalance SRV. Yeah, just China and India. So in the next figure, we want to test our hypothesis. On the first row, we have period R0 on the x-axis and the number of kin k for different types of kin in different panels. And on the second row, we have R0 squared on the x-axis and also k for different types of kin. So each circle here is the number for different countries at using different year vital rates. On the background, we also got a gray line, which is a reference line with slope 1. So when the dots lie on the gray line, we can say our hypotheses are supported. Otherwise, it's not well supported. And the result shows that our hypothesis for most types of kin are supported, except for misses. This kind of makes sense because we only calculate the number of misses when focal is between age 15 and 35. But it's very likely that focal will have new misses after age 35. So our calculation kind of underestimates the number of misses. And that's why the k is smaller than R0 squared. Yep.
I mean, we see a small, I guess, bias in daughters as well. Is that due to some preferences in China and India?
My thought is it may due to like the increase in mean age at birth, because now there are more and more women reproduce maybe after age 35, and that's why we also underestimate this part.
Oh, so this is only between age 15 and
Yes,
35.
everything is between age 15 to 35. Now we move to the time-invariant model, also kinship size. So those solid line, the layout of this figure is exactly the same as the first one. And the solid lines are still the result from time-invariant model, which we have seen before. But there are like new dashed lines on the background, which shows the result from a time-invariant model. So when we compare the solid and dashed lines in the same country, let's say the top panel for aunts in China, the red solid line changes more dramatically than the dashed line. And this makes sense because the solid line is a time-invariant model, and it's like Josh just said, it's a static model, and it kind of exaggerates the fluctuation and the change in the demographic transition. But on the other hand, the dashed line is from the time-invariant model, and to calculate the number, the king size at each year, we need to consider the vital rates for the past many years. So even though there could be a fluctuation in R naught, it will be smoothed out if we just take everything into consideration. And also, all the previous results are based on a period perspective. We just choose 1 year and look at the king size at different ages. But for the time-varying model, we could also look at it from a cohort perspective. We just choose one birth cohort and follow the number of kings for this birth cohort at different years. So the following figure, still kinship size, but one from period, one from cohort. The solid lines are the one from period, which is the one we have seen before. And for the solid lines, the x-axis is year. But sorry, for the dashed lines, the x-axis is year. But for the solid lines is the one from a cohort perspective, and then the x-axis means different first cohort. It's not surprising for us to see that these two perspectives give us different results. And for example, for China, from a cohort perspective, the number of aunts first increase and decrease, but from a period perspective, it increases over time.
Could you just remind us what the cousins and the answer? This is the maximum number that is
Yes.
observed.
Yeah, maximum expected
Okay.
number of living king.
What I would have expected, just like the growth rate of the population during the demographic transition is increasing and decreasing, and the number of surviving children and the NRR is increasing and then decreasing, to see that kind of pattern in kinship that is closely related to surviving children. Is the reason we don't see that because we start in 1950 and that's too late, or is there something about my intuition that is wrong?
I think that trend depends on which type of king we are looking at. Like for aunts, if you look at the birth cohort in 1950, their aunts is not determined by the vital rates in 1950, but way back before. So I think the trend you're talking about is correct, but could be a lagging if we look at different types of king. Does that make sense, or like?
I guess maybe the question is, if we go back in time, say in India,
Mhm.
is the green line going to go down a lot for cousins, do you think? Should it go up and then down with the demographic transition? Or maybe it's too hard to say.
I think it's. I cannot give an exact answer here.
Okay.
But for India, I forgot to say, India is like a special case because the demographic transition in India is very gradual. So if we compare the green solid line dashed line here, no matter which model we're using, the results are quite similar because it doesn't matter, the vital rate doesn't really change. But for China, it could change, like the period, people in the same time and people in the same cohort, they're experiencing different things. So I think that's the main takeaway we want to get from this figure. And then naturally, since we got the K for cohorts, we want to see whether there's a correlation between that K and the cohort R naught. So we plot the cohort R naught on the right. The x-axis is different birth cohort and y is R naught. But just simply comparing the solid line on the left and solid line on the right is really hard to find the direct correlations between the two. So we want to plot the K against cohort R naught and see whether we could get the relationships. First, we just simply applied the hypothesis we had for the time-invariant model to the time-invariant model. So still, we got cohort R0 on the x-axis for the first row, and then the k for different types of king on the y-axis. And on the second row is our cohort R0 square, and then the cohort k for different types of king. And we can see the hypothesis works well for the number of daughters, because for first cohort, the number of daughters depends on the R0 of that first cohort, which is understandable. But we don't really expect the same hypothesis works for other types of king. One simple reason will be, if we just look at ounce as an example, the number of ounce of a particular birth cohort is related to the R0 of ounce mother's birth cohort, which is the grandmother focal, instead of the R0 of focal's birth cohort. So that could be why the hypothesis doesn't work. By keeping that in mind, we adjusted our hypothesis. So for the number of ounce, we plotted with the R0 2 generations back instead of a focal's own generation. And for number of sisters, we plotted with the R0 1 generation back, and keep the daughters the same. And for nieces, we first go 1 generation back and then the same generation, because we need to first go to focal's mother and then focal's sister, which is the same generation as focal. And for cousins, it's 2 generations back and then 1 generation back. And in this figure, we assume generation time is as 25. Sorry.
I wonder if it might be interesting to, instead of using R0, which goes all the way up to infinity or 45 or something, why not just use a truncated R0 that goes up to 35?
Oh, okay.
And then it also would capture some effect of changing timing. If births are shifting to later, then a smaller share of them will be in the classic R0.
Try that. Yes. We adjust our hypothesis. It's still not really. How about we change that number? So we try not work. We're happy to take any suggestions if you have any. Just go back an average cohort of the positive instead of just go back to 1 number. Model. We note that we can either look at the result from a period or from cohort perspectives. And the result from the 2 perspectives are pretty similar if demographic transition is. And also we ask, when should we use a time-invariant model and when to use time-variant model? From the result, same for like India, when the R0 change is very gradual, we could choose either one, because the results are similar. But for cases like China, time-invariant model is unreasonable. It's like not the actual truth. And we should use the time-invariant model. And some of the hypotheses based on time-invariant model are supported, also works in a time-invariant setting, like the one for daughters or nieces. But we are not clear what the right hypotheses are for other types of kings. And in the future, of course, we need to further explore the result from time-invariant model. And also we could look at other age ranges of focal. Instead of the demographically dense ages, we could calculate the K for when focal is at sandwich ages or old ages. And then since we get the data we get from model is the expected number of living king as a function of both focus age and king's age. So instead of get the number of king at different ages of focal, we could calculate the mean age of king at different ages of focal and see whether the king also aged over time. And the effect of SRB is not included in the current study. We just assume that the SRB is the same for different countries at different year, which is not true. And it will definitely have has effect on these countries. And as Josh asked before, the demographics stochasticity is not captured in the model, but we can do that using other methods like branching process or migration. So instead of getting an expected number of king, we could get the distribution of the number of king. In the end, we could also use random matrix methods to include to consider the environmental stochasticity, like the impact of COVID-19 pandemics, which is an environmental shock and will affect the white rates. So this is the end of my talk.
Well, we are exactly on time. We have lots of time for discussion.
Happy to take any questions.
If you're in chat, feel free to type in a question, and then we have facilities somehow. I think maybe, we'll be able to ask a question. But let's start with the room. Do we have? Let's start with students this time. Do we have a question from students to kick us off? Yes, Ben.
I guess why not and specifically as the countries to study?
I think like for China, it undergoes a very rapid demographic transition, and India is the other case, is like a gradual transition. And for Japan, it has already finished the transition. So they're like in different regions.
I have a technical question. Did I read correctly that you assume in this model that mothers have zero future fertility?
No, actually, Eagle will have both older sister and younger sister. So after Eagle is born, the mother can still reproduce.
Okay, then I misread it.
Yeah, I just combined them together to get sisters.
Can I,
Yes.
please, Alice?
The generation length seemed very short to me, and I would think that it would be better to try to calculate the mean age of childbearing as the generation.
Yes, the generation time is just like a rough assumption. We could certainly change a number, also make it like different for different countries, maybe, or for different birth cohort.
But Alice, you were thinking something more like 30 is what you would have guessed?
Well, in my historical work, it was 27, but
Oh.
now I think it's becoming a little younger.
Mhm.
People are finishing earlier in India.
Because the birth cohort we are analyzing is 1950 to 2000, so that's why we think maybe it could be 25 for the on average. All of them.
25 would be better than.
Question about, we're going through this demographic transition. There's, Ron has some nice graphs in his paper of 3 centuries of demographic transition where he shows simultaneously the different kinds of dependence ratios.
Mhm.
Some are going up, children down for adults, and they go in opposite directions. And the way in which they co-vary is very important for thinking about how many kin someone has at a moment in time and how that changes over the demographic transition. Have you thought how, like, my understanding here is these things are calculated one at a time. Well, I can't just add them all up, or could I? If I wanted to know what's aunts and nieces, or grandmothers and grandchildren at the same time, kind of the co-occurrence of young and old kin.
I think you can add them together because the result we get is the number of different types of kin at different ages of focal. So if we just fix one age, then we got the number of, like you said, aunts and the number of nieces for the same focal, we just add them together. Then
Yeah.
that's the total
So this
number.
would be interesting, I think, to look at over the course of the demographic transition, because then you could see, well, how does the kind of care burden, depending on some can need care or resource change with all of them added up. And you could pick different sets of people to add up at the same time and show
Yes,
that.
that's,
I guess the related suggestion is, maybe I misread this, but the NRRs are starting at a peak and then falling in your time period, because you're starting in 1950. So you're not actually seeing,
don't have data before 1950, but we could
but you're
try.
just using vital rates.
Yeah, we
and
could
You
try
could
the
take
H1B.
Nigeria from 1950 to 2100 in that UN projections or something like that to get the whole range. You're only seeing, I mean, all these countries are having the same thing happen to them at the same time, just different levels.
Yeah,
So you're not seeing that kind of turnaround.
yes, that's a good suggestion. I should include like other countries who just started the transition.
Yeah, and then you can go into the future to get,
Mhm.
because the projections are there.
And when you talk about like combining different types of kin together, it's kind of similar to the idea, like if we look at sample, we may want the daughter's focal, how many support focal needs to provide.
I wanted to go back to a question Josh, I guess, maybe started with, which is the dispersion, the variances. And I'm, in my mind, I'm trying to contrast extreme cases. So if we have an R naught of 1, if you assume every woman has 1
Yeah, in that
birth,
moment, yes.
then there's 0 sisters. If we assume every woman has 0 births except for 1 who has all the births
Yeah,
in
yeah.
China, then there are an enormous
Yes.
number of
Yes.
sisters, but they're no cousins. And so
Exactly.
on. And that suggests, I mean, with more reasonable cases, that this dispersion, somehow you'd think it has to enter in somehow.
Yes, we think it will be like important future work. Like Toja and Wenyin, they had a study on the ALS distribution. So R naught is just the mean value of the ALS, but actually the distribution is not a normal distribution. Like especially for plants, some of them just have 0. A lot of them have 0 offspring, and then very few individuals are very successful and have like 1,000 offspring. So maybe in the human population, it's not that extreme, but still the distribution of the vital rates are important and should be included when we calculate the kinship networks. But I'm not sure how to extend the current model. Maybe we should use like, we could try like the methods listed here, like microsimulation.
There's a paper by Preston about sizes of number of daughters and number of sisters. If you guys, it's pretty well fit. I can give it to you later, but
Okay. Thank you so much.
Great, we have other.
Well, I know Ken had
We have some
several
questions in
questions.
chat
Yeah,
here.
yeah.
Here we are. Does somebody have access to the chat? Who's
I
in the
think
room?
I can open it
We can
here.
put it
No?
here or there.
There we go.
Scroll up.
can make
You want
it
to do
bigger.
this, Josh?
Sure. Oh, I can use the mouse here. Okay. So welcome everybody to the brown bag. It's very.
Make the whole window bigger too, Josh.
Thank you. Okay, so here we have Ken. Heterogeneity in family sizes across subgroups would make matrix calculations for cousins, et cetera, invalid. Doesn't this problem undermine applications to India and China? Comment, which is from the 80s onward, matrix models for kinship were largely superseded by agent-based microsimulation models, upper in parentheses, SOCSIMP, which handles lines of males and females, heterogeneity, step can, and changing rates in an easy way. What advantages do you have over agent-based models? So this is just a general question, and maybe you could answer it you could answer it intellectually, you could also answer personally. Why did you begin with this approach as opposed to the microsimulation approach?
It's a good question. Why do I choose the matrix models? Realistic reason will be it's easy to learn the matrix methods. Like it's more familiar method to me. For micro simulation, I need more time to learn it. That's a real reason. But I don't mind to learn it later because I think it's a very useful method and it could give us more information.
Right, and then there's a question from, I'm not going to pronounce the name, Ki Hui. For the time invariant model, the period but the Japanese results show an increasing trend. Using better data would create a detailed picture would be better. I think the question is about the annual fluctuations as opposed to your, I think you were taking, decade averages or maybe 1 year. Yeah.
I
So
could do it annual, like for each year.
yeah, and I'll just put in a plug for if you want to incorporate, if you figure out a method for doing variances, the human fertility database has these
Annual.
these
Yes.
cohort tables that have parity distributions. And I think there's a book by Wolfgang Lutz that has historic parity distributions, and I think Jim Vopel may have also done some early work in that. So there are some published work for that. It would be, which would be, at a minimum, you could do some hypothetical calculations like Ron was doing and say, look, the kind of errors we're making or the kind of underestimates would be of this magnitude with human distribution.
Yes, we are actually trying out the same calculation using the HMD data for Sweden because they have the vital risk back to 1700. It's still exploring it.
Great. Okay. Do we have other questions from the room? Thank you so much for a wonderful talk.
Thank you so
And-
much.
We don't have Zoom master. I think it is Maria who's remote, right? She's going to turn us off. Let's see. Are we being recorded?
Yeah.
Are we being recorded?